Welcome back. In the last video we were discussing about properties of Z transforms. We have seen two such properties. Let us look into some other properties. Let us look into some other properties in this video and along with inverse transforms before we apply this Z transform technique to solve difference equations. So, let us look into third property that we want to do. This is analogous to this convolution. So, convolution of two samples. First I define what are those two samples Fn and Gn, G of n. So, F star G of n, this is by definition. So, the same way we do this convolution I define as sigma f of n minus m and g of m is running from 0 to infinity. So, this is how I do. So, I take one function n minus m, other function m. So, you sum it up with m is running from 0 to infinity. So, this if you have this form, so if this is your convolution, a Laplace transform of Z transform of f star g of n, this convolution is actually is equal to Z transform of f of n as a function of z, this is also function of z, times Z transform of g of n as a function of z. Okay. So, this is this we can easily see a proof. So, this what is the if you actually see the domain of this convolution Z transform as a function of z, where is this validity of z? This is a common domain between validity of domain of this Z transform of f and Z transform of g. So, the common, so intersection area, intersection domain of these both the domains is actually the domain of definition for this Z transform of this convolution of these two samples. Okay. So, let's do in it's easy way. So, since f of n is 0 and g of n is also 0 if n is negative integer. So, we can think of this Z transform, we can think of f convolution g of n is actually same as running from m is from minus infinity to infinity, f of n minus m g of m. Okay. So, n is running from so this is same as that. Okay. Because if you consider any negative powers, that will become 0 if you choose. So, I can work with minus infinity to infinity. Then you apply Z transform of f convolving with g of n as a function of z is simply applied by definition, n is from 0 to infinity, this f convolving with g of n times z power minus n. So, again this if I have n negative, this is 2 or 0, n negative, this is also 0. Okay. If this convolution is this, then f convolving with g of n is 0 if n is negative integer because of this. Okay. So, if n is negative integer, m is running from minus infinity to infinity, and g is if this is positive and this will be negative in that case. If n is negative, m is positive, still you can get only positive side. So, n is if n is negative, for example minus 1, and if n is negative integer. So, f of n minus 1 m, n minus 1 m is always negative. So, that is because of this is 0. So, any negative n, this is 0. Okay. As you can easily see. So, because of this, now this definition I can extend it as from n is from minus infinity to infinity, f convolving g of n z power minus n. So, now I write the definition of this convolution inside that. So, minus infinity to infinity f convolution this I write it from m is from minus infinity to infinity, f of n minus m g of m, that is for f convolution g, and it with z power minus n. So, what is the next step? Next step is just to change n minus m as r. So, in this index if you change n minus m is m equal to n minus r. So, if I put m equal to minus infinity, r is n is also minus infinity, m is also minus infinity, n and m both takes minus infinity to plus infinity. So, r also will take minus infinity to plus infinity. So, let me write this. So, z power minus n, inside this if I take r, if I replace m by r, m by m plus r. So, r is the index now. So, m is n minus r, n is fixed. For each fixed n here you have m is varying m is varying means r is varying, m is varying from minus infinity to infinity. So, so is r minus infinity to infinity. So, you can write f n minus m as f of r times g of n minus r. No, so again you are getting back the same. So, let me not use this technique. So, what I do is I simply write this, I interchange these sums, because this sum is because once it is finite, this double sum is convergent sum. So, you write this, interchange these limits. So, you have this one and you have g of m, and inside g of m is nothing to do with n is from minus infinity to infinity. I interchange these two sums. So, you have f n minus m z power minus n. So, this is what into this is what you have if I interchange. Now, this is equal to m is from minus infinity to infinity, g of m times z power minus m will give me, I know that this is z transform of g of m. So, this times if I multiply this, I have to multiply with z power m. So, that I will add it here, f of n minus m z power minus n plus m. So, that is minus n minus m. Okay. So, this n minus m if you put as r, so r is also running from minus infinity to infinity. So, this you can replace with r. So, this is nothing but, so you can see that m is minus infinity to infinity, g of n. So, you can write n as anyway dummy. So, g n z power minus n times this is, now if I can replace r equal to minus infinity to infinity, f of r times z power minus r, because n minus m equal to r, and then n is running. So, you have n is for each fixed m you have n is running from minus infinity to infinity. So, r is running from between minus infinity to infinity. So, you have to write n equal to r plus m. Anyway, it is not required. So, we have n minus m. So, there is nothing, it is not, this is not required. So, if I change this r as a dummy into n, this is with the n. So, this becomes simply z transform of f of n as a function of z times z transform of g of n as a function of z. So, this is exactly what you want to prove. So, this is simple to prove this property. This we can use make use to find the z transform, z inverse z transform of certain complex valued functions, which you can find using this convolution theorem, just like what the same thing we have done for Laplace transform and Fourier transform. If you recall, there also we can use this convolution theorem to find the inverse Laplace transform. So, the same technique we use here. So, where is the domain of validity? Domain of this, so z belongs to domain of capital F of z intersection domain of capital G of z, where capital F and G are z transforms of small samples Fn and Gn. Okay. Fn, Fz, Zz are Z transforms of the samples Fn and Gn. So, this is the domain of this intersection. So, that is where this is valid. Okay. So, we will look at we will see other properties. This is one we use. Other one is just like in the similar to what we have done for the Laplace transforms. We can also have some initial value theorem and final value theorem. So, let us look into that. So, what is these versions here? Initial value theorem, if you see, is actually simple. So, if Z transform of the sample Fn as a function of Z is capital F of Z, then F of 0 initial value, that is there is similar to what we have done there. So, this is actually limit of there S tends to infinity F bar of S, right, that is what is the initial condition there, initial value theorem. So, here we get Z goes to infinity, here F of Z. So, this is very simple to prove, proof is straightforward. So, what we have is and also if F of 0 is 0, then you can also have F1 easily as a limit Z goes to F of Z. So, this is also you can get it from this. This is a deduction from out of this initial value theorem. So, we will see these two in this proof. So, what we do is what we know is this Fourier Z transform of the sample as F of Z, capital F of Z is n is from 0 to infinity f n Z power minus n, and then this you write it separately. This if you write, this is equal to F of 0 plus F1 of F1 by Z plus F2 by Z square and so on. So, what happens to this if you take this Z limit, Z goes to 0 infinity, you end up each of these will become 0 because Z goes to infinity, you end up F of 0. So, if F of 0 is 0, so this is clear, this is very simple, straightforward. Okay. So, if F of 0 is 0, then capital F of Z is equal to F1 of F1 by Z plus F2 by Z square plus F3 by Z cube and so on from this. Okay. So, this means Z into F of Z. Now, if you take the limit Z goes to infinity, this is actually equal to F of 1 because all other terms Z into this is going to 0 as Z goes to infinity. So, this is immediate from the definition of the Z transform. This that is called the initial value theorem version, the discrete case, in the discrete case. Okay. This is the Z transform initial value theorem, and the same way you can get the final value theorem. That is what we have seen for Laplace transforms, final value theorem, but this is not the same. You cannot it may not be the same that we have done in the Laplace case. Final value theorem. This tells you that if f of again, so if Z transform of f of n, this sample is a function of Z is f of Z, capital F of Z, then limit f of n as n goes to infinity, this is same as the limit Z goes to 1, Z minus 1 times f of Z, capital F of Z. So, this limit will give you this f infinity, which is the final value. Okay. So, how do I do this? To do this, let me consider, proof is a little tricky. So, this is if I consider this Z transform of the difference f n plus 1 minus f n, this sample, two sample differences if you take, because of linear property which is a trivial as a Z transform of f n plus 1 and minus Z transform of f of n as a function of Z, of course, everything is function of Z at the end. So, this is equal to f of n plus 1, you can use make use of first property, that is Z times capital F of Z. Okay. and then minus what is n plus 1, n plus 1 is okay. So, this is not n minus m. So, if you use this property property 1, if you use, what is the property 1? We use this one here, f of n plus m is simply z power m times for z transform minus the remaining items up to m minus 1 items in the z transform, you negate it. So, that is what you have. So, if you do it, z is z1, so z times f z minus it is 1, so up to 0 terms. So, that is f of 0, okay. And then this is for this, and you have minus capital F of z. So, what you have is here is z minus 1 times f of z minus z times f of 0, small f of 0, sample value. So, what happens now if I multiply? So, you write what is the z transform of left hand side. So, this implies the left hand side is by definition n is from 0 to infinity f n plus 1 minus f n times z power minus n, that is the definition, which is equal to z minus 1 f of z minus z times f of 0. So, this you can think of writing as a partial sums m goes to infinity sigma n is from 0 to m f of n plus 1 minus f n times z power minus n, this is equal to z minus 1 times f of z minus z times small f of 0. So, this gives me what this you can easily calculate if I put z equal to 1. Okay. So, if I take now both sides limit z goes to 1. So, what happens here, this if I take z goes to 1. So, the what you get is the whole thing, if you consider z goes to 1, this is nothing but limit z goes to 1 z minus 1 times capital F of z, and here you get f of 0 because z goes to 1, that is the value. Now, what happens to the left hand side, this part you can write as f m plus 1, everything gets cancelled. This is when once I allow this z goes to 1, this is simply 1, and you end up getting as a limit m goes to infinity sigma n goes to m f of m plus 1 rather n plus 1 minus f n, first of all this, and this implies this limit m goes to infinity. This sum, if you actually do this summation addition, you start with n equal to 0, this is f1 minus f0 plus f2 minus f1 and so on up to fm plus 1 minus fm, and the earlier term is fm minus fm minus 1. So, gets goes like this, end up, and you see that this goes here. So, you end up getting this term and this term will remain. So, you have f m plus 1 minus f of 0 equal to this limit z goes to 1 z minus 1 times capital F of z minus f of 0, small f of 0. So, this is a finite quantity, this is just from your sample. So, you can cancel both sides. So, you end up getting limit of m goes to 0, this quantity is itself. Okay. So, your limit only goes here up to here. So, this means f at infinity, this is same as a limit f n as n goes to infinity is same as limit z goes to 1 z minus 1 times capital F of z. So, this is your final value theorem. So, this may be useful when you apply difference equations. So, as and when it comes, we can make use of this in the applications, just like what we have done in the Laplace transform case. Okay. Let us find these are the typical properties that we have for Z transforms. Now, let us see what is inverse Z transform given complex valued function f of z with the domain of definition. So, let us give inverse transforms. So, let us look into inverse transforms, inverse z transforms. So, what we have is start with one. So, let us find z inverse of e power 1 by z. This is valid everywhere we have seen. Okay. So, for what function you have, if you remember, if I take 1 by n factorial as your sequence, n is from 0 to infinity, then you have seen that e power 1 by z is your e power 1 by z is a z transform. So, z transform of this is e power 1 by z. So, z inverse of this is actually goes, this is what it is. You can directly, if you remember, you can do it. So, otherwise what you do is to get this e power 1 by z, you try to expand this 1 plus 1 by z plus 1 by z square 1 by 2 factorial and to 1 by z square and so on. You write like this. This gives what is your f of n? F of n is so this is sigma n is from 0 to infinity, some constant, that is 1 by n factorial times z power minus n. So, this is your z transform of this quantity is actually this. So, this is one way. So, this implies z inverse of e power 1 by z. This is a trivial thing. This is as a function of n is simply 1 by n factorial. So, n is running from 0, 1, 2, 3 onwards. 0 factorial is 1. So, second example, let us look at inverse transform of z transform of inverse z transform of z into z minus, or rather z by z minus a as a function of n. So, this is again you do not have to remember z by z minus a. You have seen already a power n. If you consider z transform of this, you have found that this z by z minus a, okay, where the domain of validity is this, mod z is greater than a. So, this one, to get this, you start with the function z minus a. So, z and divide by z, you take it out and you have 1 minus a by z. So, if you do like this, a by z has to be less than 1. So, that means mod z is greater than a. Okay. So, mod z is greater than a. So, clearly, so if it is given, once it is given like this, validity of this, they should be given. So, where mod z is this, what is find just like finding this, where this is this, then only I can write a by z. Otherwise, I may have to use z by a. If mod z is less than a, I have to choose z by a, then only z by a is less than 1, then only I can expand this 1 over 1 minus z by a, because this is z by a is less than 1. So, here a by z is less than 1, that is clearly because of this mod a by z. Okay. Mod a by z is actually mod you have to choose, mod a by z is less than 1. So, because of that, if z goes, you have 1 by 1 minus, so this is 1 by a by z inverse, mod a by z is less than 1. So, I can write a by z plus a square by z square and so on. So, what you have is simply a power n z power minus n, and n goes to 0 to infinity. So, this is z transform of a power n. So, this implies, so this is z inverse of z by z minus a is equal of as a function of n is a power n. N is running from 0, 1, 2, 3 onwards. So, this is one simple thing. So, and the third one, you can also use partial fractions to find the z transforms. Okay. Z inverse of f of z, where f of z is as a function of n, where f of z is, let me write as z by z square minus 6z plus 8. So, how do you get this? So, if I write this f of z as z over, it has two roots, the denominator that you can write z minus 3 and z minus 2 and z minus 4. Okay. So, that you have a minus 6z. So, that is what it is, and this you make a partial fractions to see that this is going to be 1 by z, z by z minus 4 minus z by z minus 2. So, if you actually see that z square minus 2z minus z square plus 4z. So, the 2z comes up. So, you have a z here. So, you have 2 to cancel. So, this is the form for this. So, if you try to get this z inverse of f of z as a function of n, this is again it is if z transform is linear, z inverse is also linear. So, you can because of the linear property, z inverse of this half times z by z minus 4 minus z inverse of half times z by z minus 2. So, this is half comes out because of linearity again. Z by z minus 4 is a power n. So, you have 4 power n, and you have here for this you have half times 2 power n. So, this is what is your z transform, inverse z transform, okay, for every n. So, next one is you can also use convolution theorem when you have these rational functions like this. What is the z inverse of if you choose z square by z minus a z minus b. Partial fractions sometimes will give you complicated, it is difficult to find, maybe little difficult to find the partial fractions. In that case you can use the convolution theorem. So, how do I find the convolution? Convolution theorem is if I write z square by z minus a into z minus b as z by z minus a times z by z minus b. So, in this case this is my 1 and this is another function. So, this is how do I write this? This I can write as a z transform of a power n as a function of z times z transform of b power n as a function of z. And this is my given f of z. Okay, this is my given f of z. So, this is actually we know that this is actually same as z transform of convolution between a convolving with b power n as a function of n, which is a function of z finally. Okay. So, this we know by convolution theorem. So, this implies, so you take the both sides z inverse, if you take both sides z inverse both sides. So, z inverse of z square by z minus a times z minus b as a function of n is equal to z inverse of z of this z of a power n cross b n as a function of z. And once you take this inverse, this is becoming a function of n. So, what is this one? So, this z goes, you end up getting a n convolving with b n as a function of n. So, this is summation, this is should be function of n. So, you have running from 0 to infinity a power n minus m b power m, that is it, that is your summation. So, if you have this, this is your z inverse z transform of this. Okay. So, you can simplify further by a power n, bring it out. This is from m is from 0 to infinity b by a power m provided. So, once you know a and b, you know that mod a is same as mod b is if it's if they are different. Okay. So, if they are same, you cannot write like this. This is going to be infinity. So, you cannot write a by b is a by mod a is same as mod by b, mod a mod b. You have to leave it like here. So, if mod a is bigger than mod b, then this will be mod b by mod a is less than 1. Okay. So, you choose if you choose like this, so that I can write this as a power n 1 by 1 minus b by a. So, you have a by a minus b. So, this is equal to 1 by a minus b times a power n plus 1. So, this is true if mod a is bigger than mod b. So, what if you have mod a is so this same thing we can write this is also equal to, we can also rewrite like instead of writing this way, we can write we can also write m is from 0 to infinity. The convolution both sides is both are same. So, you have b power n minus m a power m. So, this is also true, and this will give me b power n sigma m is from 0 to infinity a by b power m. So, this is 1 by 1 minus a by b, that is b minus a by b into b power n. So, you have together b power n plus 1. So, this is true if mod a is less than mod b. In both the cases you can get this. Okay. If mod a equal to this is equal to sigma m is from 0 to infinity a power. So, this is usually you can keep it if mod a is same as mod b. If mod a is, so a b can be complex numbers because these are a complex function. So, if a b are this, you leave it here as it is, and if you have convolution, you can choose if a is mod a is bigger than b, you can modify this way. If mod a is less than b, you can modify this way. So, this way you can get this z inverse in all the cases, all the 3 cases. Okay. Then we look into some example. So, what is the Laplace z inversion of f of z, where f of z is 3 z square minus z by z minus 1 times z minus 2 whole square. So, use the partial fractions because the numerator is order is smaller. So, if you write this f of z as partial fractions, I get 2 z by z minus 1 plus minus 2 z by z minus 2 plus 5 by 2 times 2 z by z minus 2 whole square. So, you get something like this first initially. So, because of this square z minus 2 whole square. So, this is your partial fractions, okay, 5 z. This is how you can partially make a partial fractions, and you write this. So, z inverse of f of z, because of linear property you get as n. So, you have a z inverse of 2 z by z minus 1 minus z inverse of 2 z by z minus 2 plus z inverse of 5 z by z minus 2 whole square. So, I have seen earlier that this is 2 comes out, you write 2 outside because we know z by z minus 1, what is that one. So, here also you can take 2 outside because of linearity. So, you see that z inverse of this we know already that this is 2 into 1 power n. So, that is 1 minus 2 into here this is 2 power n. Okay. So, this second thing is this part is 2 power n, and what about this one? This is also again 5 by 2 times you can write z inverse of 2 z by z minus 2 whole square. So, this one you can you have seen already that z transform of n into 2 power n is actually equal to, you have seen that this is the, if I use this one n into 2 power n as z transform of this is equal to minus z times d dz of z transform of 2 power n, that is z by z minus 2. So, if I do this, you have minus z times 1 by z minus 2 minus plus. So, you have a minus here z times you have if you z plus z, this will be minus z square, and this will have 1 by z square, right. 1 by z minus 2, if you differentiate, you get a minus sign, and you have this is what you get. So, if I use this, you have z minus z times, numerator is z minus 2, and here minus z. So, minus z plus z goes here, denominator z minus 2 whole square. So, you have 2z by z minus 2 whole square. So, that is what we can use here. So, you can see that 2 minus 2 power n plus 1 plus 5 by 2 times. So, you can write z inverse of this is n into 2 power n. So, if you remove this, you have n minus 1 for 5 times. So, this is validity. So, this is your z inverse. And then let us look into some other examples. Like this, you can go on doing z inverse of for example, z into z plus 1 by z minus 1 power cube. This you can this also you can write, you can find this. So, how do I write this? Z into z plus 1 by z minus 1 cube. I make a partial fractions here. First I write z minus z by z minus 1 whole square into z by z minus 1. So, because I know this one, okay, and also I know this part, okay. So, these two I know, this one and this one. So, I write it as first term. A second term I write it as z by z minus 1 whole cube. So, I write first as z minus 2 and the one is z minus 1. So, 1 by z minus 1, if we already know that z of 1, if you actually calculate, so you get 1 by 1 minus z. So, you have that is constant, right. So, you have z power minus n is from 0 to infinity. This is z by z minus 1. So, you have 1 over 1 minus 1 by z. So, this is z by z minus 1. So, if I choose, this is the sequence of like a h of n, okay. So, this is h of n is the Heaviside function, your sequence is 1 comma 1 comma 1. So, right from the beginning it is 1 1 1 constant. So, if I choose h of n minus 1, n is 1 onwards, it is going to be 1, otherwise 0. So, n equal to 0, it is 0 1 1 and so on. So, what is this one? Z of, so this implies z of h of n is actually equal to this h of n minus 1. If you calculate, what happens is a function of z, this is n is from 0, it is from 1 to infinity z power minus n. So, this if you calculate and you simply have 1 by z comes out and you end up getting n is from 1 to infinity. So, if I calculate this, this is same as n minus 1. So, n minus 1, if I take it as a new variable, so as m, so this is going to be running from m is from 0 to infinity. So, this is exactly 1 by z times z transform of h of z. So, this is 1 by z times z transform h of z is this. So, I have z by z minus 1. So, this gets cancelled. So, 1 by z minus 1 is actually your z transform of this Heaviside function, but it is starting from 1 onwards. Okay. So, if I know this one I know, this one I know. So, you can directly write your z inverse. Z inverse of this is actually z inverse of this. Okay. So, z inverse of both. Okay. This is a product. Okay. Z inverse of this plus z inverse of this function. So, you can make use of your I can make use of convolution theorem here. So, z by z minus 1 is 1 power n. So, that is 1, and then z by z minus 1 whole square is 2 z by z minus 1 whole square is n into 2 power n minus 2 that is n into 2 power n. Okay. So, you can write this as a half here and you can put 2 here. You can also make so that you can make 2 here, put a full whole bracket together. So, if I use this, so this is going to be half times what is this one? This is a convolution of this one. So, this is 2 z, sorry, you have to put it here. So, this 2. So, 2 z by z minus 1 square is n into 2 power n convolving with it is 1. This is h of n rather, okay. This is h of n, because h of n is z by z minus 1 plus, and here this is z inverse of this product is, this is also n into 2 power n convolving with, this is h of n minus 1. Okay. So, this is actually 1 by n 1 by 2 times n into 2 power n convolving with h of n minus h of n minus 1. So, this is what you have. So, this you actually if you simplify and see, this is actually you end up getting n square. So, for each n you will get that only n square. So, you sum it up and see that it is you will see that it is end up getting n square. So, how do I see this? So, let me do this is 1 by n into 2 power n, right. Oh, this is so okay, no, this is n into 2 power z is z by z minus 2, but I have only z minus 1. So, it is actually n into 1 power n. So, this is 1 power n. Okay. So, z n into 1 power n, that is 1. So, this is simply n convolving with h n minus 1. So, you have half times. So, 2 z by z minus 2. So, you do not really require this half. Okay. So, this 2 you need not write, because z by z minus 1 square z transform of n is actually equal to z minus z by z minus 1 whole square. So, how do I get this? This is equal to, you can think of as 1, and this is same as minus z d dz of z transform of 1, that is z by z minus 1. So, this if you do this 1 by z minus 1 minus z by z minus 1 whole square. So, if you see this 1 minus z times z minus 1 minus z by z minus 1 whole square. So, this is minus this z goes. So, you have finally z by z minus 1 whole square. So, that is simply n. So, if I use that, z by z minus 1 square is simply n. So, you do not have half. So, you have this is actually n. If n equal to 0, this is negative and this is 1 and this is 1. So, it is 1. Okay. And if n equal to 2, so 2 multiplied with 2 convolving with so h of 2 minus h of 1. So, if you actually do this convolution, let me if you do this convolution. So, what is the convolution? N is from 0 to infinity n minus m times h m minus h m minus 1. So, m equal to 0, if you put m equal to 0, h of 0 is 1 and this is only m n, right. So, you have n. If you actually sum it up, this is going to be this is the convolution, and if you convolve, this is what it is, the convolution. You have n plus m equal to 1, n minus 1 times, and you have h1 minus h0, h1 minus h0, that is what is the value of H0 is 1, H1 is 1. So, that is 0. This is simply 0. M equal to 1, H1 minus H0, and then n minus 1, M equal to 1 is this, H of 1 minus H of 0. So, H of 1, H of 0 both are 1, 1, that is 0. So, it goes, and then plus H equal to 2, M equal to 2 minus M equal to 1. So, that is also 0 and so on. So, you end up getting only n. So, this is your n. So, you should get only n. No, this is something is wrong. Oh, this is addition, right. So, we have a addition here. So, we have a addition here, not subtraction. So, this h n plus h n minus 1. So, if you do this addition, so you get n first h m. So, other one is n minus 1 times m equal to 1, this is 2, and again. So, 2 into n minus 2 and so on. So, you end up getting n plus, if you sum this up, you end up getting, so you can see that this is going to be n square. Let me convolve, this is same as, if let us see if I can easily see that m is from 0 to infinity, this is n, and this is h of n minus m plus h of n minus m plus 1. So, this is also true as a convolution. So, if I do this way, so if I do this, whether I see I get n square. So, m equal to 0, that is 0, m equal to 1, h of n minus 1 plus h of n. I will just leave it here. So, this value you can verify that this is going to be n square. This is the question we can see. You can take it as an exercise, and you see that this is what is the case. So, if you do have some rational functions like this, you can make use of known Z transforms, Z inverse transforms, and then convolution theorem you can apply and get this Laplace inversion. Okay. We will see some more examples, and we will see finally application of Laplace Z transform to the difference equations in the next video. So, we will see. Thank you very much.